Good morning, everyone, and welcome to my home office and workshop and now test hut in Minneapolis, Minnesota, where I've been working most of the last year and a half and mostly enjoying uh, living in my test building, where it makes it very convenient to make lots of measurements. So I've been measuring lots of wind pressure fluctuation measurements in my house over the last couple of months. Let's see now. Oh, I need my keyboard. There we go. And we'll just go. So I'm going to mostly be talking about field measurements that I've been doing to try to improve the measurements in windy conditions. And I'll show results from testing measuring the outside pressure at different locations and a little bit about different designs of the pressure taps. And then I'll quickly show some results from some tall buildings that were recently tested. Uh, when we do a blower door test, we're trying to measure the amount of airflow that's needed to create a given change in the pressure difference between inside and outside. So we turn the blower door on, we adjust the speed of the fan to get to a certain flow, and then we measure what's the change in the change in the pressure difference between inside and outside of the house. Uh, Physics says that if the interior of the building is one zone, in other words, there are no pressure differences across floors or walls, that change in pressure difference uh, will be exactly the same at every location where you would measure the pressure difference between inside and outside. However, there's a problem in windy weather. If the wind is fluctuating, there's noise in the outside pressure, and it turns out in the inside pressure, there's noise due to the wind, and the amount of the noise varies from location to location. So ideally, what we would like to do is find the location to sense the outside pressure where we get the smallest variations in the measured pressure differences. Uh, we at the Energy Conservatory have been, our historic advice has been to measure, to sense the outside pressure very much differently than some people recommend. We recommend that you sense the outside pressure on the leeward side of the building and right in the crack where the wall on the leeward side of the building meets the ground. We did testing many years ago on just a couple of buildings and thought that that worked the best. So I'm going to try to, I've been trying to investigate whether that really is a good idea. And of course, it's also important, as Valerie mentioned, to measure for long enough time to get stable readings. But I didn't really measure that in my study. So this is where I've been making my measurements. This is my house, and I'm on the taking this picture from the very northwest corner of my house. And this is looking at my house in the area where if the wind is blowing from where I'm standing, there are the fewest obstructions to the wind. Behind where I'm standing, there's a street. There are a few trees. And as you can see, this is an old neighborhood. So there are lots of trees and plants around the buildings. You can see that there's a house very close to my house on the south side. There's another house not far away on the north. And in the back of the house, there's lots of trees. There's a fence over here. There are obstructions. And my experience testing buildings is there are almost always major obstructions. And it's impossible to measure someplace where you're completely away from obstructions. So during my testing, I'm measuring here. Here you can see this is the windowsill in my office. I've made holes in a brand new, very good window to permanently install pressure tubes so that I can very easily run 8 different pressure tubes to the outside and then run those to various locations on the outside of the house. And for this test, I'm always recording these 8 pressures once every second. And then once I've recorded the pressures, I look at the files and I determine 10-minute periods of time where it looks like there was strong wind, because 10 minutes is about the time that it takes to do a complete multi-point blower door test. And then during that 10 minutes of time, I divide that period into 20 30-second long periods to approximately simulate the length of time that it takes to make one pressure measurement. So I'm then going to calculate the standard deviation of those 20 30-second averages, and that will be the measure of how good or how stable the pressure is during this 10-minute period of time. So here's a plan view of the house, and I'm just going to report on one series of tests, or one test that was done over 10 minutes, but I've done hundreds, and I haven't had a chance to look at most of them. But that will be something I'll be working on in the near future. So for this test that I'm going to report on, we have a wind coming from the northwest at about 6 meters per second, and I'm sensing the outdoor pressure at 8 different pressures, and we'll see those in the next couple of slides. I'm also simultaneously measuring with a very sensitive barometer the barometric pressure inside the office in my house. And my house is about 850 cubic meters and about an N50 of 1 air change per hour at at 50 pascals. So when I'm making these measurements, there really aren't pressure differences between rooms. Most of the doors in the house are open. There aren't, well, occasionally my wife is turning a kitchen fan or the dryer on, or somebody is, but most of the time the pressures inside of the house are fairly uniform. So we'll later talk about the readings from this barometer, which I found were quite interesting. So the pressures on the outside of the house, first I measured 4 pressures on the east, north, west, and south sides of my house. This is a garage, and this is a porch that's on a crawl space. And I'm measuring these with a T fitting that's located right where the wall and the ground meet. And I designed a T fitting using about a 12 millimeter inside diameter tube, so that it does what a regular T does, but it also holds the end of the tube up above the ground, so that if it rains, it keeps the rain from the water from getting in the tube. And I've had these tubes outside my house for a couple of months, and none of them have plugged yet with water. So then I'm also measuring at 2 different locations away from the house. Here we see the number 5 and 6. Here I have a 2-meter tall pole that near the top there's this red thing, which is a commercially available from Dwyer Instruments. It's a static pressure sensor that's designed to go on above the roof of a building to sense the reference pressure for a building pressurization system connected to a commercial building ventilation fan. These are available from a bunch of different manufacturers. And then at the same location, I'm measuring the pressure down on the ground, also with a T fitting, but the end of the tube is kind of pushed into the grass, so it will be damped maybe a little bit from the grass. And then the other location is on the about 8.5 meters to the northwest of the building. Again, about 2 meters above ground. I have a T on the end of a pipe that's facing straight up, and the top of the T is approximately perpendicular, in this case, to the direction of the wind. And just below that, in the ground, on the ground again, there's another T fitting measuring at the ground level. So I think I've already talked about this. I logged the data every second. I then generated 10-minute periods representing a full blower door test. I divided that into 30-second averages to represent approximately the averaging time for an individual measurement, either the zero pressure measurement or the pressure during when the fan is running. And then I'm calculating the standard deviation of these 20 30-second averages. And here we see the results of those readings. And you see the average pressure in pascals, which I think isn't a very important number, at least for evaluating the quality of the location as far as wind pressure fluctuations are concerned. The number that really concerns us is the standard deviation. Excuse me. And you'll see that the lowest standard deviation was actually measured over here on the leeward side of the building, right where the wall and the ground come together. And the highest standard deviation was located the furthest away from the building, where I'm trying to get as much as possible into the undisturbed wind stream, where theory seems to say that we should see smaller fluctuations, but in fact, I measured the highest fluctuations there and the lowest fluctuations over on the leeward side right next to the building. You can also see it's interesting on the west side of the building. So this is also right at where the ground and the building come together. We have about a Pascal of pressure, but even there, it's better than the variations here right at where the building and the ground come together are less than the variations up 2 meters above the ground in the more undisturbed wind. So my conclusion is that and others have concluded this also, that one thing you want to do is you really want to get out of the velocity pressure. You want to get out of the dynamic fluctuating pressure, and you want to get out of the wind. And an interesting thing is I said that I had the lowest fluctuations where I was on the downs. Oh, I'm going to skip this one. I'm running out of time. And I think I'll skip this one. So some next things that I'm going to be working on is testing various configurations for the end of the tube where we're sensing the pressure. Here you can see I've got T's in 2 different directions. And this is something that I discovered just last week. If I take a disc and drill a hole in the middle and attach a pressure tap there and then suspend this disc about 5 millimeters above my patio, that seems to give me a much lower standard deviation. Unfortunately, I didn't have very high winds, so I used a fan to blow air across it, and I need to test this with some real wind. And here's that Dwyer static pressure sensor. Whoops, I'm running out of time. I compared it with a T and with a straight tube. And then at the ground level, I have a T on the grass, and I also drilled about a 10-centimeter deep hole and then sealed a 5-centimeter long tube in the hole to sense the pressure in the ground at the same location. It turned out these sensors measured almost identically the same pressure. A quick note about the barometric pressure. This yellow line is the barometric pressure fluctuations. Of course, the barometric pressure is actually 100,000 or so pascals higher than this, but I'm subtracting that off so that we can see the fluctuations on the same scale. And this is that same 10-minute period of time that the table of results was for. The white line is the lowest standard deviation measurement location. The green is the highest standard deviation pressure measurement location. And you can see that the yellow, the actual pressure inside of the house is varying more than the pressure difference measured at any of the locations where we're measuring the pressure difference between inside and outside of the house. I don't have any conclusions about this, but this is something that I really want to think about some more. And uh, I've always assumed that the pressure fluctuations are larger outside the house when you're in the wind than it is in the variations in the barometric pressure inside the house. I'll say one other thing about tall buildings. This is from a paper that was just presented at the Passive House Conference a few weeks ago by Stephanie Rolfsmeyer and Emmanuel Meringer, an engineer from Vienna, where they tested 3 35-story buildings recently, and they measured the pressure difference between an inside and the outside at the top of the building on 4 sides of the building, on the 22nd floor just on one side, on the 12th floor on 2 sides, and at the ground floor on 3 sides. And this is the zero pressure measurement over 2-minute period of time. And these are also 1-second averages. And you can see, oh, you really want to measure the pressure at the bottom of the building. You don't want to be measuring and doing calculations on the pressure at the top of the building. And then we ensure that there aren't pressure differences between the top and the building by measuring internal pressures and adjusting fans so that the building is in the single zone condition. And that will be the end of my presentation. And I don't know if there's time for questions, maybe 1 or 2.